Hello friends, this is my first video regarding the mechanical engineering, and the topic that I am going to talk is the stress strain diagram. So I am going to talk about the stress strain diagram. Okay, for particularly I will talk about the ductile material. I will talk about the ductile material. Okay, so the stress strain diagram that we obtain after we perform on any kind of material after we perform the tensile test. Okay, so how it looks, let us see. Okay, so on x-axis we have engineering strain, and on y-axis we have engineering stress. When I say engineering, it is totally different from the true stress strain curve. So particularly right now I am talking about the engineering stress strain curve. So we have one y-axis, we have one x-axis. On x-axis we have engineering strain, and on y-axis we have engineering stress. Now see how the graph looks. Okay, so this is how the graph looks. Okay, let us consider the points on the graphs. So first point that we have on the graph, let us say this is A, this is B, this is C, this is D, this is E, and this is F. Okay, so now let us know all the points with their name. That point A is known as the proportional limit. It is known as the proportional limit. Why it is known as the proportional limit? Because up to point A, the stress generated in the material that is proportional to the strain generated in the material. Okay, up to point A, the stress while testing, the amount of stress generated in the material or the specimen will be proportional to the strain generated in the material, and that is nothing but the Hooke's law. This is the statement of Hooke's law, that strain is proportional to strain. Okay, and we are talking about engineering stress strain curve. So that is the first point. Point number B, that is known as the elastic limit. That is known as the elastic limit. Why it is known as the elastic limit? Because if we load the material till point B, the material will be able to regain its shape and size. Okay, so the material is loaded within the elastic limit will be able to regain its shape and size, and that's why it is known as the elastic limit point. Okay, then we have point number C, that is the upper yield point. Upper yield point. Then we have point number D, that is lower yield point. Lower yield point. Yielding means deformation of material. Okay, the permanent deformation of material starts after B. Okay, so yielding you can consider as the permanent deformation. Okay, now we have two yield points, point number C and point number D. Okay, the upper yield point, that is unstable in nature, while point D, that is the lower yield point, that is quite stable in nature in comparison to C. And that's why when we design any component using the ductile material, for design purpose we use D as the reference. So lower yield point is considered as the what we can say maximum allowable stress for the ductile material. Okay, and if we design any material which is brittle in nature, and for that we consider UTS as the maximum allowable stress. Okay, so upper yield point and lower yield point are the two yield points, out of which C, that is upper yield point, that is unstable in nature, while D is stable in nature, and that's why we consider point D, lower yield point, while designing any mechanical component which is made of ductile material. Then we have point E, that is the ultimate tensile strength, and that is known as UTS, and that is the maximum stress, or we can say the strength that a material can possess. So UTS, the point E, is the maximum value of stress that the material will be able to sustain, will be able to bear before failure. So after that we have point F, that is the breaking point. So here at point F, the material will break into two pieces. Okay, the specimen will break into two pieces. Okay, so these are the points. Now let us go into the detail that how this graph can give us different what we can say region. So there are certain region in this graph. So let me draw that region. So first region, this region till point B, that is known as elastic region, because the material is loaded within the elastic limit. Up to point F, okay, up to point F, this region is known as plastic region, because after B the plastic deformation of the material starts after B. So this is the plastic region of the material. Okay, and up to B, that is the elastic region of the material. Okay, so these are the two regions, one is the elastic region and one is the plastic region. Now if we go in detail, then this region DE, this DE line, that is known as strain hardening. And this EF curve or EF line, that is the necking region. So there are four main regions. One is the elastic region, one is the plastic region, then the strain hardening region DE, and then EF, that is the necking region. So in plastic region we have strain hardening region and necking region. Okay, this C to E or B to D, we can say B to D, that is the abnormal behavior of material. Okay, Here we get in B to D, we get abnormal behavior of material. From B, there is the plastic deformation start. Plastic deformation start means the material, if it is loaded beyond the point B, it won't be able to regain its shape and size, original shape and size. Okay, so these are the points. Now this let us consider this point as O. This OA is a straight line. Okay, and this OA line represents the Hooke's law, which is the stress proportional to the strain. Then we have the point B. So let us say this is how the specimen looks, for tensile test specimen. This is how it looks. Okay, it can be a rod, it can be a strip. Okay, and one end is gripped in the machine, while on the another end is also gripped, but one end is a fixed end while another end is the moving end. Okay, so we are applying load in or we can say we are applying the displacement in this direction. Okay, and the speed by which this end, the moving end, moves, that is known as the crosshead speed, or we can say the testing speed. According to the standard, we have to maintain the speed. Okay, so we get we have gripped the specimen and we are applying the deformation when we move this end. So initially we will get the strain produced in the region, or in the specimen, that will be proportional to the strain. If we go beyond point A, the stress and strain will increase, then it will slightly, strain will increase in comparison to the stress. Then there will be sudden decrease in the stress. Okay, and there will be large amount of strain in the specimen. Okay, in the material. Then again there is a rise in the stress. So here there is a question, why after decrease, why there is a rise in the this graph D2E, why there is a rise? So the reason behind that, when we deform the material, okay, the material that is made of lattices, okay, that is made of lattices. So when we initially deform the material, this dislocation of lattice happen, or dislocation of atom happen. Okay, so this is how the atoms are arranged in a specimen. Okay, so the dislocation of atom happens inside the material, but this is up to certain limit. After certain deformation, this dislocation of material resist each other. Okay, the dislocation movement is resisted by its own lattices. So to deform the material, we need to apply more load. Okay, so there is a sudden rise in this value of stress because we have to apply more load. Okay, since we apply more load, the amount of stress, the magnitude of stress increases. So this phenomenon is known as strain hardening. So how we can define the strain hardening? Up to certain limit, when the material is loaded, the dislocation movement, okay, is easy, is smooth. But after some point, after certain limit, this dislocation movement is resisted by its own lattices, or we can say atoms. Okay, and because of that, there is a sudden rise because we have to apply more load. When we apply more load, the amount of stress increases. So this region is due to the strain hardening, that is known as the strain hardening, that on lattices, on atoms are resisting the dislocation movement. Okay, that is known as strain hardening. Then we have this necking region. So this here, if we focus, so after the material reaches to its ultimate limit, means point E, there will be necking, means like this. Material will begin to deform like this. So the here the cross section area will decrease. Okay, so the load carrying capacity of the material decreases, and that's why we get this decrease in this EF line. Okay, and at the end the material will fail like this. It will be like, not exactly like this, but somewhat like this. Okay, this is known as cup and cone fracture. This is cup and this is cone. This is known as the cup and cone fracture. Okay, and this is only possible in the case of ductile material. All these things are applicable to ductile material. If we test the brittle material, we won't get this kind of what we can say stress strain diagram. Okay, so the stress strain diagram for the ductile material is completely different than the stress strain diagram of the what we can say brittle material. Okay, so the 6 points are very important, and there are main two region, elastic region and the plastic region. In plastic region, we can say we have distinct strain hardening zone and necking zone. Okay, and between B to D, we can say that is the abnormal behavior, okay, of the material. Okay, so this is the stress strain diagram for the ductile material, we can say. Now let us say how it looks for the brittle material. Okay, how it looks for the brittle material. So let us consider stress strain diagram for brittle material. So if I have to draw, then it will be like this. Again we will have, so in this case you will have done. This is the nature of the graph for the brittle material. Okay, here engineering strain, here engineering stress. Okay, so this will be the UTS of the brittle material. So there is no necking, there is no yielding. Okay, only there is the UTS point. Okay, which is the maximum stress that can be taken by the material. Okay, so this is how the what we can say the stress strain diagram for the brittle material looks. Okay, since it is brittle, there will be no plastic there will be no elastic deformation. Like brittle material, if I have to give the example, brittle material like chalk stick, okay, the day-to-day, then we can say the brick. These are very brittle in nature. So if any metal is having this brittle property in it, it will fail like this. Okay, so in this case we will not have any necking, we will not have any yielding. Okay, and the material, the specimen will fail like this. It will fail like this, simply separation. Okay, it will be simply separation. Okay, so if I have to, what we can say, see the blue line is for ductile material, and this yellow line is for the brittle material. So this is the difference between the stress strain diagram of the brittle and ductile material. But this diagram are, once again I have to say, engineering stress strain diagram. Okay, so I hope this is clear to you. In my next video I will come up with more detailed understanding of stress and strain, which is very helpful for the competitive exam as well as for the interview. Okay, the interview of any mechanical engineer will begin with this kind of questions. So these are the very basic and very important questions for any mechanical engineer. Let it be a diploma engineer or degree engineer or master degree engineer. It can be anything. Okay, but these questions and these concepts are very basic. So I hope this was helpful for you. Okay, thank you very much.